welcome you in the lecture series of Basics of Communication Engineering, and this is tutorial 4th based on lectures 8 and 9. The question first is determine the transmission efficiency and the percentage of the total power carried by the sideband of amplitude modulated wave for single tone modulating signal when m is or modulation index is 0.5. So here first point is to find out the transmission efficiency. You know the transmission efficiency eta is m square by 2 plus m square. So from here we can find out 0.5 square by 2 plus zero point 0.5 square, and it will be equal to 0.1111, or you can say it is 11.1%. And second is the sideband power. Since the total sideband power in it is equal to m square by 2 pc, because the transmitted power is the pc 1 plus m square by 2. So it is pc plus m square by 2. Pc is the power in the carrier, and this is the power in the sidebands. And so I can write PSB sideband power by PC, it is m square by 2, or you can say it will be 0.5 square by 2, or it is 0.125. So the sideband power in percentage, it is 12.5%. Now the next question is, a sinusoidal carrier has amplitude of 10 volt and frequency 30 kilohertz. It is amplitude modulated by a sinusoidal voltage of amplitude 3 volt and frequency 1 kilohertz. So modulating amplitude is 3 volt and frequency 1 kilohertz, and carrier having the amplitude 10 volt and frequency 30 kilohertz. The modulated voltage is developed across the 50 ohm resistance. So first point is determine the modulation index. Write the equation for the modulated wave and plot the modulated wave showing maxima and minima of the waveform, and draw the spectrum of the modulated wave, and also calculate the total average power and calculate the power carried by the sidebands. Here you can see AC is 10 volt and FC is 30 kilohertz. So here from the question, AC, the carrier voltage is 10 volt and carrier frequency is 30 kilohertz, and AM, the peak amplitude of the modulating signal, it is 3 volt and frequency of the modulating signal is 1 kilohertz. Now the first question is, what is modulation index? You know the modulation index M is equal to AM by AC, or you can write it is 3 by 10. So the modulation index is 0.3. Now the second point, it is you have to find out the equation for the modulating wave. You know xct, the model equation for the modulated wave, it is AC 1 plus mxt cos 2 pi fct, or we can write it as AC 1 plus m cos 2 pi fmt if xt is cos 2 pi fmt and cos 2 pi fct, or we can write it as 10 1 plus m is 0.3 we have calculated here, and cos 2 pi fm is given 1 kilohertz, so it is 1 into 10 is to the power 3 t, and cos 2 pi and fc is 30 kilohertz, 30 into 10 is to the power 3 t, or we can write it as 10 1 plus 0.3 cos 2 pi plus 10 is to the power 3t, and cos 6 pi 10 is to the power 4t. So this is the equation of the modulated AM wave. And now the modulated waveform. So the modulated waveform will be, here the A max is AC plus AM. AC is 10 and AM is 3, so it is 13 volt, AC 10, and A minimum, A minimum is AC minus AM, AC minus AM, so it is 10 minus 3, 7 volt. So A minimum is 7 volt and A maximum is 13 volt, and M is 0.3, so it is under modulation, so the A minimum will not be 0. You can see A minimum is this 7 volt here, and this is the envelope of the signal AC1 plus MXT. It is the envelope of the signal, and this is the modulated carrier. Now the another point is spectrum of the modulated wave. The sideband frequencies are the upper sideband. You have upper sideband frequency will be 31, because frequency of upper sideband, it is FC plus FM, and FC is 30 kilohertz and FM is 1 kilohertz. So it is 31 kilohertz. And the lower sideband frequency, it is FC minus FM, so 30 minus 1, 29 kilohertz, and center frequency will be FC, this is 30 kilohertz. So at the center the carrier wave of 10 volt, and the upper and lower sideband having the frequency 29 and 31 kilohertz, and the amplitude of each sideband, the amplitude of sideband, it will be M by 2 AC. M here is 0.3, 10 by 2, so it will be 1.5 volt. So here the amplitude is 1.5 MAC by 2. If AC is 10 volt, then the amplitude of the lower and upper sideband, it is 1.5 volt. So this is the spectrum of the modulated wave. And now total average power of AM wave. So the transmitted power, it is the carrier power PC into 1 plus m square by 2, or we can write it as the carrier power is AC square by 2 RL. Load resistance 1 plus m square by 2. The load resistance is given 50 ohm and AC is 10, so you can write it as 10 square by 2 into 50, and 1 plus 0.3 square by 2, so we will get it is 1.045 kilowatt. So this is the transmitted power, and part F is the total sideband power. It is m square by 2 PC, m square by 2 and PC. So m square is 0.3 square by 2, and the power in carrier AC square by 2 RL, and it will be equal to 0.45 watt. This is the total sideband power. Now another question, for AM DSB FC double sideband full carrier envelope with plus Vmax is 20 volt and plus V minimum is 4 volt. Determine the following: peak amplitude of the carrier, the modulation coefficient and percentage, peak amplitude of the upper and lower sideband frequencies. So first is peak amplitude. From the lecture, the peak amplitude of the modulating signal AM, or you can say VM, it can be calculated from, if A max or V max is given, A max minus A minimum by 2, or you can say V max minus V minimum by 2, and it is 20 minus 4 by 2, 8 volt. And the peak amplitude of the carrier VC, it is the average of V max and V minimum, so it is 20 plus 4 by 2, and it will be 12 volt. So the peak amplitude of the carrier, it is 12 volt. And second point is the modulation coefficient and percentage. The modulation M can be calculated from V max minus V minimum divided by V max plus V minimum. So here 20 minus 4 by 20 plus 4, it is 16 by 24, or you can say 0.667. So it is the modulation index, and in percentage form you can write it as 60.7%. So the modulation index M is 60.7%. And another point is peak amplitude of the upper and lower sidebands. The peak amplitude of the sideband, it is peak amplitude, it is m AC by 2, or you can say m VC by 2. It is 0.667 into 12 by 2, and it will be 4 volts. Now another question is, draw the spectrum of an AM signal with the carrier CT is AC cos square pi FCT, and the modulating signal XT is AM cos square pi FMT. We know the CT, I can write it as AC by 2 1 plus cos 2 pi FCT, and similarly this xt can be written as am by 2 1 plus cos 2 pi fmt, because cos square theta, it is 1 by 2 1 plus cos 2 theta. And now the spectrum of xt, the Fourier transform of xt, using Fourier transform we can get the spectrum of xt. So Fourier transform of xt, it is fxf, or Fourier transform of am by 2 1 plus cos 2 pi fmt. And so here I can write Fourier transform of am by 2 plus Fourier transform of am by 2 cos 2 pi fmt. And the Fourier transform of this, it will be am by 2 delta t impulse function, and this is am by 2 Fourier transform of cos, it is 1 by 2 del f plus fm plus del f minus fm. We have this Fourier transform, so we can sketch the Fourier transform as this. Here you can see am by 2 del f at frequency 0 and am by 4 at frequency f plus fm and f minus fm. So the amplitude of the side bands is am by 4. Amplitude of the centered frequency, it is am by 2. So we have centered frequency at 0 for the modulating signal, and amplitude is am by 2, and signal having frequency fm, the amplitude is am by 4 del f plus fm. This is am by 4 for minus fm. So this will be the spectrum of your modulating signal xt. Now the spectrum of am signal, CT is given as AC by 2 1 plus cos 2 pi FCT. So this carrier having the DC component AC by 2, and the Fourier transform of this DC component, it will be AC by 2 del t. So the Fourier transform of this AC by 2 cos 2 pi FCT, it will be AC by 4 del F plus FC plus del F minus Fc. So now the spectrum of the modulated signal can be here. This is the carrier frequency Fc and minus Fc, and for which the amplitude for the carrier, it is AC by 4, and the bandwidth is the difference between upper sideband and lower sideband, it is 2 fm. This is the spectrum of AM signal. Now another question is, consider the message signal xt 20 cos 2 pi ft volts and carrier wave ct is 50 cos 100 pi t volts. Derive the expression for the resulting AM wave for 25% modulation. Here xt is given as 20 cos 2 pi t, and after comparing it with AM cos 2 pi fm t, I will get FM is 1 Hertz and AM is here 20 volts, and CT is 50 cos 100 pi t. Comparing it with AC cos 2 pi FCT, I will get FC is 50 Hertz and AM is 50 volts. And here modulation index M is 75%, or I can write it as 0.75. So now AM wave, amplitude modulated wave, it is AC 1 plus M xt cos 2 pi ft into cos 2 pi fct. This is fmt. And here I can write 50 1 plus 0.7 cos 2 pi ft fmt and cos 2 pi fct or we can write 51 plus 0.7 cos 2 pi t and cos 100 pi t. So this is the amplitude modulated signal. Now next question is, a simple diode detector used a load resistance of 400 kilo ohm. Across the resistance there is 100 picofarad capacitor. If the maximum modulation depth of the input amplitude modulated signal is 70%, what is the maximum frequency of modulating signal that can be detected without diagonal clipping? So here the time constant RC is given. R is 400 kilo ohm and capacitor is 400 picofarad. So it will be equal to 4 into 10 is to the power minus 5 seconds. This is the time constant. And without having diagonal clipping, the time constant RC can be less than equal to 1 by 2 pi Fm and into 1 minus m square and root of this divided by 2, and RC is given as 4 into 10 is to the power minus 5 less than equal to 1 by 6.28 Fm 1 minus 0.75 whole square by 2, and from here we can have the relation Fm, it will be less than equal to 3510 hertz. So you can say this is the frequency of modulating signal or maximum frequency of modulating signal. Here this is the answer of this question, what is the maximum frequency of the modulating signal without diagonal clipping. So this is the maximum frequency 3510 hertz. Now next question is, sketch the modulating signal x omega given that xt is cos 100t or xt cos 100t plus 2 cos 300t or cos 100t cos 500t. Here if I compare cos 2 pi fmt, it is 2 pi fm 100, or you can say it is omega m is 100. So the for the xt cos 100t, the x omega, it will be it is in this figure, and for the second part it is having two frequency component 100 and 300. Omega is 100 and 300, so we can have for 100 and 300, and here amplitude for the 300 is 2 times for the amplitude for 100. So here we have written the amplitude for 100 is pi and amplitude for 300 is 2 pi, and third part is cos 100t and cos 500t. Using the formula 2 cos a cos b is equal to cos a plus b plus cos a minus b, it is given xt cos 100t into cos 500t. So we will get the two frequency component at 600 and at 400 using 2 cos a cos b is equal to cos a plus b plus cos a minus b. So the frequency components at 600, 400, minus 400 and minus 600. Now the next question, prove that the upper limit for RC is less than equal to 1 by omega m under root 1 minus m square by m. The capacitor is charging and discharging. This is discharging time through the load resistance. The capacitor discharge from the peak value E to the starting at some arbitrary instant t0. The voltage Vc across the capacitor, and it will be Vc, across the capacitor, it will be E is to the power minus t by RC, time constant. So peak value E, and this is going to discharge from peak value E, and it will be approximately, I can write E 1 minus t by RC. By using Taylor series we can have this, and the slope of the discharge is minus here minus E by RC. In order to follow the envelope ET, to follow this envelope, the magnitude of the slope of the RC discharging must be greater than the magnitude of the slope of the envelope ET. That is, we can say dVc by dt mode of this, it is equal to E by RC, and it should be greater than equal to dE by dt mode. Since ET is A, 1 plus m cos 2 pi fm t. Now det by dt, it will be minus ma 2 pi fm sin 2 pi fm t. And so we can write here a 1 plus m cos 2 pi fm t by rc. It will be greater than equal to m a 2 pi fm sin 2 pi fm t. And from here we can have rc is less than equal to 1 plus m cos 2 pi fm t by 2 m 2 pi fm sin 2 pi fm t. And the worst possible case occurs when the right hand side is a minimum. This is found to be when the cos 2 pi fm t is equal to minus m. And for this case the right hand side is this will be equal to 1 minus m square under root by m 2 pi fm. So rc will be less than equal to, so here it will be equal to rc less than equal to 1 by omega m 1 minus m square under root by m. This is the proof of this upper limit of rc, time constant rc. And this is the end of tutorial 4th. Thanks for listening this tutorial. In the next lecture we will discuss about the double sideband suppressed carrier amplitude modulated signal generation and detection.